So this is example 1 in module 5. Again, I'm going to assume that you've already worked this problem. The example is about a space heater. Space heaters are just appliances that turn electrical power into heat. And the example here is a 1500 watt space heater. So watt is a unit of power. This is telling us that the space heater uses 1500 watts of power. Now the actual space heater might look something like this, right? There's some that have large radiating plates, some stands, there's a cord that comes out here, it's got a plug, and then that goes into the wall. But really all I need in order to answer this question is a circuit diagram of the space heater. And so the space heater is plugged into the wall. The wall is a voltage source, so the wall acts as the EMF or the power supply or the battery. And the symbol that we use for the EMF is a long line next to a short line. The space heater itself dissipates power because it's a resistor, so it is resisting electrical current. There must be current that runs through it while it's operating, and so we can represent the space heater as a resistor. So this space heater has some resistance, which is what we're looking for in the first part, and it's connected to an EMF or a voltage supply that has some voltage, which I'll use a sort of a curly E to indicate. Now, since this is an appliance that's going to be plugged into the wall, we know that the voltage of the wall, well, at least in the United States, is 120 volts. So whenever I have an example or a problem that tells me about something that I know is going to be plugged into the wall, or it tells me that it's plugged into the wall, I'm basically told that the voltage that is applied across the circuit is 120 volts. So I know that this is 120 volts. Now we know the power that the space heater uses, and we actually have 3 different formulas that we can use for the power. They are all equivalent. One is that the power is equal to the current times the voltage. Another one is that the power is equal to the voltage squared over resistance. And another one is that the power is equal to the current squared times resistance. So this is the power that is used by a resistor. The version that we use just depends on what's most convenient at the time. I mean, they are all equivalent. You can get all 3 of these, you can show that all 3 of these are equal to each other if you use Ohm's law. So Ohm's law says that V is equal to IR. Alright, well, if I take V is equal to IR for my first power equation, I get the last power equation. So they're all the exact same thing. It just depends on what we know. What we know will determine which one of these is going to be the most useful. So in the first case, what is the resistance of the space heater? Well, I know what the power is, so I'm going to use an equation that involves the power. I want the resistance, so I'm going to use an equation that involves the resistance. And then I know the voltage, so I'm going to use this equation here, because that relates the power to the voltage and the resistance. Alright, so the power, which is 1,500 watts, is equal to the voltage squared over R. That means that R is equal to the voltage squared over power. So this is going to be 120 volts squared divided by the 1,500 watts. 120 squared is 14400, so 14,400 over 1,500, and that's volts squared per watt. And that gives me a resistance of 960. So 9.60, and that's going to be in ohms. So the ohm is the standard base SI unit for resistance. Volts is the SI unit for potential difference or voltage, and then watt is the SI unit for power. So as long as I stick with the base SI units, then volts squared over watts is going to give me ohms. So the resistance of the space heater is 9.6 ohms. The next question asks, how much current does the 1500 watt space heater draw when it is operating? So you turn the space heater on and it draws current from the wall. How much current is it drawing? Well, we know again that it dissipates 1500 watts of power. We know that the resistance now of the space heater is 9.6 ohms, so we could actually calculate this in a couple of ways. Let's look at the first way. The first and easiest way would probably be to use the power equation that just involves current and voltage, because I know what the voltage applied across the space heater is. So the current is going to be the voltage divided by the power. Oh, wait, hold on, I got this backwards. Let me delete this. Delete this. Current is going to be the power over voltage. So that's 1500 watts over 120 volts, which is 12.5 watts per volt, which is going to be 12.5 amps. So the current is 12.5 amps. The other way that I could have calculated this would be to use the power equation that involves current and resistance, because I also know the resistance. So power is I squared R. I squared is P over R. So the current is going to be the square root of P over R. So I've got 1500 divided by 9.6, and I take the square root of that, 12.5 amps. So I should, of course, get the same answer regardless of how I calculate the current. And that's it. That's the answer here. So if we know how much power the appliance dissipates, and we know what the voltage that it's connected to is, we can determine how much current it's going to draw, and we can determine what the resistance must be.